possible, but I don't want to go into very intricacies at the moment because I'll share my phone number at the end, and I don't want any of you to save my number as Professor Bohr or Professor something. Okay, so I'll try to keep this a bit interactive, and let's try to get some knowledge on nanomaterials and such. How many of you are already aware or have some information about nanomaterials, about nanotechnology? You guys have some information, some knowledge. These people have worked for Smita anyway. People PhDs on nanotechnology. And okay, so I quickly plugged in some slides. Unfortunately, ours is a very hectic schedule. I don't know, we always keep on running. Okay? So unfortunately, because of my leg, my running has become a bit slow. I actually had an accident. But anyway, so let's start. You can see the slides, right? Or is it too bright? Is it okay? Alright, so we all love our own area of research, right? So definitely for me, I'm very passionate about nanotechnology as such, and I try to sort of convince everyone that yeah, this is something very important. Maybe you should put in some interest as well. Okay, so personally, I am involved in nano research since 2005. So it's almost 2 decades now. Okay, so whatever knowledge I've gathered over the 2 decades, I'll try to share in 2 hours with all of you. And let's try to understand the importance of this. I'm not very sure if you are familiar with these faces. Are you? Maybe in the news? Anyway, these 3 scientists recently got the Nobel Prize in chemistry. Okay, and for what? Yeah, for developing the quantum dot. Okay, which is basically the smallest nanomaterial, that has been prepared by man. Okay, so they were working in quantum dots. Okay, so I'll come to that in details later. What is a quantum dot? But basically, you can say that this is a nanoparticle. Okay, that means its dimension is very small, maybe 2 nanometers, 3 nanometers in diameter. Okay, and they behave differently, uniquely. Okay? So all these, our LED TVs, okay, anything related to LEDs now in display units is because of these quantum dots that these 3 scientists have jointly developed. So one is from MIT, he is now in Columbia, and Alex, these 2 are Americans. Alex is a Russian, and but see, he works in the US in a nano company based in New York City. Okay. So just to give you a rough idea of what we are talking about in terms of size. Okay. So we are talking about this quantum dot, which is basically about a few thousand atoms together, maybe any atom. Okay, but typically it's mostly semiconductors we refer to as quantum dots. Now, if I compare that to a football, quantum dot and a football, the size difference, that means the number of times the size, it will be the football compared to the earth. Okay, so that is the size we are talking about. If you take a football and you compare it to the earth size, then the nano particle like the quantum dot, it is similar to the football. Okay, so that is the size we are talking about. Anyway, nature has been doing this for billions of years. Okay, the first established nano scientist is nature. Okay, and we simply are at the moment trying to mimic nature. Okay, when I first started my research in nanotechnology back in 2005, at the time I was in the Asian Institute of Technology, which is in Thailand, and we really didn't have a lab as such. Just me and a couple of others, 3 or 4 of us started the research, and we had nothing, right? There was no lab. Oh wow, more Don Bosco. Nice to see you guys. Actually, at home. All right, so we started from scratch, and when I was reading others' papers and everything, trying to understand about nanomaterials, my first, you know, thought was that this is beyond my capability, not because of my intellectual prowess, but because of the facilities that other people are writing in their research papers. I say, no way, this is for the rich. Okay? This is for the rich universities with sophisticated facilities. Otherwise, this is not possible. Okay? That was my feeling at that time. And then I remember my boss, we used to call him boss, he said, any idea how many nanomaterials are there in nature? I said, not really. I haven't studied natural nanomaterials. And he said, go ahead, study a bit. And when I was doing that study, I said, oh my God, nanomaterials are everywhere. And nature has been doing for billions of years. I said, okay. I told him that these are the things I found out. I said, good. So where are the sophisticated facilities for nature? Where are those sophisticated labs that nature is using? None. So if nature can do that, why can't we do that? So that was the first, sort of a motivation to study and mimic nature in making nanomaterials. Okay, applying them is a different thing altogether after that. But anyway, okay, so this is a scale bar. Just to give you an idea, because most of you are already aware, when we are saying nanometer, we are talking about 1 billionth of a meter, right? 10 to the power minus 10 meter. And typically, it's not very rigid, the definition about nanomaterials. It's typically we say that it is less than 100 nanometers in any of the 3 dimensions. It may be in all the 3 dimensions, it may be even in one dimension is less than 100 nanometers, we still consider that as a nanomaterial, but that's not very rigid, okay? I mean, bigger materials are also considered to be nanomaterials. So, nature has been doing this. This is the range we are talking about. Okay, so we'll have all this biological stuff. Okay. So DNA is of that size range. There is 1 nanometer that nature is making. Okay. Even the red blood cells, you see, they're much bigger. Okay, they are, a few hundreds or nanometers. That is roughly the range of micrometers. And similarly, human beings, mimicking what nature has been doing, they have also come up with unique materials in the nano size. Okay, we even have, even though this is like pictures are from MEMS, micro electromechanical systems. Okay, where real working systems. Okay, the gears all move. Some scientists even designed a steam engine where the individual components are in micrometers. That means thinner than your hair. Okay? But now we have gone far ahead. We are not talking about MEMS anymore. We talk about NEMS, or nano electromechanical systems. Okay? So that means these arms and everything, they have gone to nanometer sizes now. And human beings have been able to do that. Okay? So we have been able to manipulate material. We have been able to pick up atoms, place them where we want. Okay? So it's very exciting. And we talk about novel materials or new materials now. Right? New materials, new properties. Okay? So now when we're saying new materials, I remember I think this was in Stanford University. That was 2017. I was invited to deliver a talk there, and also in UC Berkeley. In Stanford, one student asked, we are talking about new materials, so many new properties. We have been studying materials for so long, right? So where do you think your new material will come in into the periodic table? Okay, we all know about the periodic table, right? So it's like all elements are placed here based on their atomic number, right? So this students here ask me, where will you plug it in? There's no space left in the periodic table. Okay, so that is not what we are actually talking about. We are not talking about individual elements or atoms. We are talking about a few thousand atoms together, right? And these atoms are picked up from the periodic table. It's nothing new. Nothing new, believe me. It's the same material. Only thing is that we can now play around with the material. We can plug in the atoms here and there. It's not like so much of freedom, but we definitely can do that. And obviously, when we are doing that, we are trying to modify the properties. And these properties we will take into our advantage and go for applications. Okay? So, all right, let me try to further convince you. Yeah, my students, they've always seen these slides. At one time, I used to love making slides. So nowadays, I don't really have the time. So I still plug in those old slides. Anyway, this is the thing that we all know that we have damaged our ecosystem, the environment. Earth is no longer healthy, all right? And we see so many sci-fi movies where they show us 50 or 100 years later, the Earth is gone. We are looking for other settlements, right? So we are doing the damage. It's totally us. So why are we doing that? Why are we damaging? Maybe initially unknowingly, but now even after we know that we are damaging, we are still doing it. Because there's no way out. Think of crossing Maligaon or Jalukbari in your vehicle without an air conditioner in summer. Is it possible? Honestly, it's literally impossible for us. Now we cannot even think about it. Nowadays, I don't think we have non-air conditioned cars available in the market, right? Because it's getting hot. It's getting hotter and hotter. And precisely, we all know that there's a huge contribution of freon that is used in the air conditioners in, global warming because they are eating away the ozone layer and whatnot. So we know that. So ultimately, what is happening? Global warming is happening. We are using more and more air conditioner. So in more and more heat, ultimately, it's a vicious cycle. We cannot come out of that. We need the air conditioners. Okay. So when you get this electricity bill at the end of the month in summer, that's quite shocking actually. For me, it is quite shocking. But because of the use of air conditioners. Now, we know this, yet we have been using the same technology. Why? Mainly because we have not been able to find out an alternative technology that is more environmental friendly. As simple as that. We know it. And that's why I say that scientists all over the world have been spending so much of time on research. So if things are not happening, then at the moment, the current technology being used by people cannot do it. As simple as that. No, it's nothing that there's something left to be explored. When we talk about electronics, so we talk about circuit design, VLSI. No, honestly speaking, I don't think any circuit left in the world that has to be designed. We have already done that, right? Anything you think about it, we have done it. What we are currently doing now, we are trying to go on miniaturizing because we need more and more, you can say, possibilities using the electronic gadgets we have. Right? This stupid cell phone, we call it smartphone, but I still prefer to call that as a stupid device. Okay, but think about it, we cannot survive without that now, right? We cannot survive. We definitely, it's a very important part of our life. The first thing after getting up is, those who don't have specs can directly pick up. Those who have specs may have to find the spec, put up and look at your phone, right? I also do that. So it has become a parcel of our life. So we are using it. Fine. But think about the speed. Those who have gone through, because I bought my first cell phone in 2000. Okay. So it had an antenna coming out like this, right? Now it's no more. You don't see the antenna in your cell phone anymore, right? There again, all these are happening because of progress in nanotechnology. Your phone has now maybe 4 processors. Some even may go to 16 processors. You know, each processor is working independently. We expect so much from these processors, and believe me, now it's about like a 1 billion or more transistors in each processor. Fine. That means phone size is not becoming bigger and bigger, right? It's still there. And if you open the cell phone, 80% is because of the battery, correct? Think about it. If the battery technology had been going at a fast pace like the rest of semiconductor industry, then the cell phone would have been here. You don't even need to do it. You just say call, it will call, right? So how is this happening? Billions of transistors. Previously were in here, now it is, you don't even see the transistor. Okay, currently Intel is going down to maybe 5 by 5 nanometers for one transistor. Okay, your human hair, look at the tip of it. You can plug in now a few billion transistors and wire them, connect them also. Okay, and all are working with, you know, one typical clocking maybe or two clocking. It's unthinkable, believe me. All right, but like I said, you know, when you are transforming something, you know, but you have to use existing technology. The semiconductor industry, you know, is still working with silicon. Fine. It's not that there are other options not available. We have studied so much on optional semiconductors. All right. So many prospective semiconductors are there, but why are we not doing it as yet? It's because of the amount of infrastructural investment that is needed. Think about it. You know, facility already built up with billions and billions of dollars. All of a sudden you say, no, we're going further down. This technology cannot help us. We need new fabrication units or fabs, and let's invest another $100 billion. It's a commercial thing altogether. People are buying the cell phones. Today, you know, Apple anyway is very expensive. But even then, if your regular phone, all of a sudden from 20,000, it goes to maybe 1 lakh, how many would be able to afford it? So that's another point. So market will go down. So you have to use the existing technology. That's why we are thinking more and more as to how, using the existing technology, we can try to incorporate more and more functionalities in our devices. Okay, I'll show you how a few things on how these are happening. But this is what I was talking about. This you know, global warming thing. It's happening anyway. So we have no choice, but we have to find out other options. Nanotechnology, I won't say it is like a, you know, don't worry, go ahead and use type of a technology. Any technology coming in, it will have its certain implications which you need to take care of, right? So once you know that, you can always manage to do that. But if you don't know, then of course a lot of things might happen. Okay, so you know, I don't know, maybe these things happened before or not, but the frequency has been increasing of late. We hear so many things about tsunamis and all those, right? Too many. Maybe that's nature's way of telling us that you better behave and, you know, enough is enough. I won't tolerate anything more like this. Okay? So a lot of these things are happening now, and a lot of human life gone. Okay. So I think my students have seen these slides, some of you. So another thing is the energy part. Right? Like I said, battery technology is not going very fast. Your cell phones are still very big. Right? We know about alternative sources of energy. We all talk about solar energy, but we are not using it. I mean, to the limit that we can. We are not replacing, you know, our regular fuel that we are using. We are not replacing with solar as yet, right? Because why? Because the current technology that we are using is not being able to deliver the amount of, you know, efficiency that we need to completely replace the existing energy source. Because we need huge amount of energy. All of us, if you think about it, all of us are using so much of energy every day. been in various forms. Okay, you're driving your vehicle, your electricity at home, the pumps that are running for your water, the refrigerator, so many things. Yet, we have not been able to go solar. We have not been able to go wind. We are doing it, but at a much lower, consumption level. So we have now come up with this type of a phenomenon here. This is Los Angeles. It's an old photo, and this is in Beijing. And this is actually not fog. Okay? So this is a new thing. New thing in the sense that this has been included in the dictionary now. It's called smog. Okay? SMOG. It's a smoke and fog coming together, and it's really, really, I can say, difficult in the sense that it does not, because the fog, it vaporizes when a lot of sun is coming, but this one hangs a few meters above the ground, and we're constantly inhaling that. You know the situation in Delhi recently, of late, especially in winters. So that's why this photograph is seen in the same location after some amount of rainfall. Okay, so this has all settled down. Okay, all has settled down. That means there were suspended particles. That rainfall pulled down to the soil. Okay, so we are constantly being inhaling this. I don't know what is the status of our lungs, but something to worry about. So, looking for alternative sources, these are the things I mentioned. We already have nuclear, solar, wind, okay? So many different sources. Hydroelectricity we are using, but the amount generated, because hydroelectricity has to be transmitted through wires, but now we are doing a bit wireless also, but still the efficiency is not that great. Okay, so we need these replacements. We all know about it, but we have not been able to do that mainly because the supporting technology is not able to give that much of, you can say, conversion into usable energy. But all these, nuclear is good, but even then, many countries still avoid nuclear. Why? Because of, like I said, some implications that it might be dangerous. And it has proved to be dangerous also. I don't know if you know this place called Chernobyl. That's in Russia. Anyway, I'll show that. So we are seeing renewables just about 13% of the total consumption of energy, and out of that, only about 0.5 are coming from hydroelectricity and other forms of energy. Okay? So that is the catch. The current technology is not able to support us. So, this is the thing in Chernobyl. There was a huge explosion, and the radiation is still there. It seems it's a dead city. Many people died. Okay? But have we been able to stop that? I mean, we are still using nuclear because that's a huge amount of energy being generated. So, only thing is we need to be playing safe. The same with nanotechnology. We really need to know what are the possibilities of its effect on the human life, on the ecosystem, on the marine life, everywhere. And then we can, if known properly, we can definitely take the necessary precautions, okay? And avoid disasters like this. But these are huge things. This doesn't happen with nanotechnology. It's considered to be a very, very green technology. Okay? Anyway, we are very, very conscious now. A lot of shouting, publicity. So newspapers speak about this. So it's not that we don't know anymore. We know what is happening. We know that we are doing the damage. We also know that we cannot avoid that. So we need that. So we need a different option, a different technology maybe, okay, that is not so dangerous for the environment. And personally, I feel this is something that needs to be explored more. Almost 3 decades now, people are very seriously going into nano, mainly because of the development of a lot of you can say machineries, tools that can help understand this. So, for those who are not aware, many of you are aware. So, this term nanotechnology, before I move to nanomaterials, this term was coined in 1974 by a Japanese scientist called Norita Taniguchi. So, nano basically means, it's a Greek word, basically means a dwarf, a small size human being or any other living being as such. So it's small. So anything, it's a small thing of already existing things. Like I told you, nothing is new here. The same things that we know before, we are just trying to restrict that in size so that we can, come up with new properties and we take that to our advantage, we use them for applications. Okay? So this is the scale we are talking about, 1 billionth of a meter, and at that size range, materials behave different. Now, we'll also discuss about a bit about fabrication. So how we actually do all these things, how we have been able to follow nature and come up with our own nanomaterials. So two ways we can do that. We can take a bulk material, break it down to nano sizes, keep on hitting it. Right? Take a hammer, start breaking it. Okay, something like that, and come up with your nanomaterial. Right? You can try that. Okay? You can take 1 year, keep on hitting, but your nanoparticles will not actually come out. Right? Because the surface roughness of the hammer head looks very smooth to all of you when you are using it, but the roughness is in hundreds of micrometers. And we are talking about tens of nanometers. The roughness is huge. If you won't even break it to that size, you maybe go down to micron sizes. So it is not so easy as it sounds. Right? But we can do it. Definitely we can do it. But for that, you might have to invest a few $100 billion in it. Then of course we can do it. Right? Because we will use very, very sophisticated tools that can actually do this. Break up bulk material into nanoparticle sizes. Okay? I was lucky to use a few of them, but nature definitely does not have those. So there might be other options also. So we can go for this process where we call it as the, this one we call it the bottom-up process, right? Where we start with individual atoms. Right? Because we say no, the nanoparticles are maybe few thousand atoms together. So that's what we do. We pick up those atoms and we place where we want. Once those, we reach the size we want, we simply stop it. Okay? Very simple. Not really, but it is possible. We do that. Okay? Because separating of atoms in a liquid is very easy. If you use salt, dissolve salt in water. Salt vanishes. Why? Because it is no longer NaCl, you dissociate them. Sodium goes, chlorine goes separate. Right? Simple. You want sodium? Just take some salt, dissolve in water, you have sodium there. Right? So if you want to use sodium for making nanomaterials, it's easily available in atomic form. Same like that. You can take any salt, right, and dissolve it in water or some other solvent, and you get. So chemically, this is very easy. The bottom-up process. So you can have three atoms, bring them together, create the conditions that they come together, and then, just stop when you get to the size you want, and it's there for you, right? But then again, also it's not so easy because very soon you'll see that everything agglomerates and goes back to the bulk condition. So we really need to see how we can stabilize these particles so that they don't come together again, don't become bigger. Alright? So mostly this is done by most of the laboratories, most of the universities that are doing nano research. Like I said initially that this is for the rich labs. The rich labs definitely have those facilities that can go for the top-down process. And the top-down process gives you accurate material. Right? You said this is the size I want, this is the shape I want. 95 to 98% will be exactly that. You are going for the top-down process. It's a very sophisticated and expensive processes. But if you go the other way, bottom up, you might not get that 90-95% of similarity, maybe 70%, but still it's okay for your applications. Okay? Because if you're coming up with actual devices for the market, for consumers, you know, you may be ready to, you know, adjust a little bit of the performance. That means you go for a top-down process, you come up with a device that gives very accurate performance, 95% efficient, and you come up with a bottom-up process that gives 85% efficiency. But the price is maybe 100 the price difference. Obviously, you'll be happy with the 85% efficiency also. Okay? So then, you know, because it all depends upon the buyers, the consumers. So that's why we actually came up with a term which we call poor man's nanotechnology. Okay? So even poor people like us can do research in nanotechnology. So this is how we make these, you know, particles in a liquid. This one. So I will, if I get time, I will explain that on the board a little bit how this happens. Okay, so all these atoms they start coming together, become bigger, and then we stop. The size we want, we stop it there, right? And then of course we use it for various applications. So I already said, no, that nature has been doing this for billions of years, and we are simply trying to mimic nature. So this is a butterfly, we call it morpho butterfly. It's a beautiful butterfly with blue colored wings, right? Now, this beautiful blue color that is coming out is not because of the presence of any dye. It's not color. Honestly, not color. That is painted. We use paints, right? All our clothes are dyed. So dyes are basically molecules that give color. Here, something different is happening. Nature has done something else here. So if I zoom into the wing now, right, you see the structuring is like this. And to observe the dimension there, these are in, so you see the scale bar, that's 1 micrometer. There's a scale bar there, right? This one. So from here to here, this is 1 micrometer or 1000 nanometers. Right? And the other parts are even smaller. Alright, so these will be like a few tens or hundreds of nanometers. So this is basically nanostructuring on the surface done by nature. And this one actually is responsible for this beautiful blue color through, because these acts like those who are, you know, comfortable with optical systems. This works like diffraction gratings. All right, very similar, you know, obstructions to light. And then what happens when light grazes over very sharp points? Diffraction happens. And diffraction basically means bending of light. Okay? And this bending, the amount of bending, depends upon the wavelength. Right? So when it grazes, obviously, you know, light, visible light is composed of so many different colors, all have different wavelengths. So obviously the amount of reflection of light will be different for different colors. Right? And the majority that reflects a particular wavelength, we see that. Right? So this beautiful blue color is coming up because of that. Is similar to what we said the sky is blue. When you look from below, but if you go up on an airplane, you will not see it blue anymore. Okay? So nature did this beautiful work. And apart from that, this is also what we call as a hydrophobic surface or super hydrophobic surface. You see butterflies, they can simply fly around even when it's raining. That means if their wings had got wet, they would have become happy. Right? So their wings never get wet because water rolls off. It's very similar to the lotus leaf structure where you see lotus leaf, you see water droplets, droplets and roll off. So they don't wet. Right? Now this is another interesting nano material in nature. This is the leg of the gecko, the lizard. Have you ever thought about it? They are upside down, moving around. Okay? You don't fall down. Only because they have these small air cups. You know air cups? If you think about it, we have these hangers or everything you place on the wall and it sticks. You cannot pull it off. So if you slide, it will come out. Things like that. Here you observe a these are moving, it will not move like this. It will move like this. The movement is flat on the surface because they are rolling those cups. And it's not just one, two cups. If I zoom into them, you see all those are individual cups. All of these, air cups. All of these. Billions of air cups here. That's good enough to support the weight even if they are upside down. Even if gravity is trying its best to pull it down, it will not come. So nature has been doing this. And this is another natural surface. This is a lotus leaf. Okay. So why water does not spray on a lotus leaf? Again, that's another nano material developed by nature. Okay. If I zoom again here, so these are the structures you see. This is a electron microscopy image. Right? So you see a lot of structures like this. These are actually micron size. And if you zoom further, all these small fur-like things on there, there's a small nano-rod-like structures. And this gives it the super hydrophobic surface because the water droplets do not get punctured here. They simply distribute the weight on these tips. Right? So this can be done, or we can try to replicate using similar nanostructures. And this is the process. So water droplets simply roll off, and when they roll off, they carry on the downstream. So that's what we call the self-cleaning concept. So nanomaterials, many nano companies, they came up with their self-cleaning clothes way back, or 10, 15 years back. They came up with their self-cleaning or always dry type of material. So an American company first started it. You drop a cup of coffee and you just walk away. Nothing happens. There's no stain, nothing, it's just falls. So, and there's no crease. It doesn't get creased, so you don't have to iron them. Right? So, that is again following the natural structures here. So, we also try to do this in our lab. Using some structures like this. So, these are cooked in our lab. Right? So, I personally cook these rods. The small nano rods. Okay? And they are arranged in such a way, they naturally arrange when I was making the sample. And then it sort of gives the same feeling like the the lotus leaf. This one. See, this is a photograph taken on a lotus. You see the green color, that's the lotus leaf. And here, this is actually these type of rods that we grew on a bandage. Right? Bandage, because we took the challenge. Bandage is supposed to be a hydrophilic. It just takes in any liquid. And we try to convert that, and we managed to do that. Okay? And we got this one. This is the bandage material with these type of rods. And you see, they also have become super hydrophobic. Right? So, this photograph actually, and this one, we took with a system we made ourselves. Right? That's the performance and technology I was talking about. We can actually develop these systems ourselves at very, very nominal cost. So it's not necessary that they buy everything. These instruments we made when I was in Don Bosco University. Right? We made a couple of very, very good instruments ourselves because we did not have the money. So no money, no choice. Right? So when I joined Don Bosco, and I was coming from Assam, which is one of the best in the Nordic region, like 18 of the laureates from that university. So obviously, whatever I wanted was there. All the facilities were there. Very, very sophisticated labs. And then I come here and there's nothing. Okay? So we then decided like this instrument that took this photograph, this one, these photographs, we wanted to buy it initially. Because we are working, because this concept is there for high-rise buildings with glass. Think about the danger of cleaning it. People climb up and they hang themselves. When you have some surfaces they don't need cleaning. That's so wonderful. You can put everything in glass if you want, and they can be opaque also, they can be translucent also, they can be transparent also. So that way, this machine, when you ask for a quotation, two quotations came, one from UK, one from US, one was about like 8 point some lakh, one the other one was about 9 point some lakh. And we didn't really have money. Okay? So I was in the electronics department, so a couple of students said, let's do this. We had a couple of lab assistants who are very good at that. Let's make this. We know what we want. We know this would be the input, this would be the output. Why can't we do this? And even with this machine that was like the quotations were more than 8 lakhs, we made it 49,000. And these are the photographs taken here. Okay. And so that actually gave us a motivation, and we said, okay, let's do this to almost another company. So we made many instruments like this, and so that's the point. That nothing can stop you. And if you think about all those Indian knowledge, they always had done their research in labs. They had become their own home in a corner of their labs. Okay, so you don't really need sophisticated stuff. You know, too many smart things make us dumb. Okay, I don't know. Think about reversing your car without a camera nowadays. I mean, previously when we reverse car, we used to look at the, sometimes look back, sometimes look at this window. Now we have cameras, right? So if you all of a sudden are given a very old car that doesn't have a camera, we might have problem. That's why I'm saying, no, more smart things make us dumb. Okay, so that's why uh, we need to think that, because I remember, once I was punished because I repaired a machine. Okay, and it was a big punishment, believe me. So I was called by the rector. That was in Sweden. Okay, and like a typical Asian, I used to work in weekends. I don't know why. We people from this part of the world, you know, Asians, mostly Asians, Indian, Chinese, then Pakistanis, Bangladeshis. We don't know what we want to prove. We work 7 days a week. We are crazy. I also did that. So all the people from the West, they know that these people will work in the lab on Saturdays and Sundays. So by Friday, most of the time by Friday, my table will be filled with food and drinks, because they are going out for fun. They said, okay, this guy will work, so leave everything. So my table used to be full of apples and cakes and whatnot. Anyway, so we used to work, and I was going into this clean room on a Friday, and I noticed that the instrument I wanted to use, it was not working because we get a report. No? The previous one who tried to use it could not use it. So he put a note that this is not working. And I had big plans for the weekend. So many samples I need to work on. So this was not acceptable for me. So I said, okay, let me think. I was looking, and then I said, okay, I think this is this. So basically, some small dust particles went into the main chamber. So I opened the chamber, evacuated it out with a vacuum cleaner, put it back, and it started working. So I was so happy. I did the work. Monday morning, I got a call from the, they say rector. It's like the dean. So rector called me. He said, you had used the microscope for, it's an electron microscope. You used it for over the weekend. I said, yes, I did. He said, how is it possible? Because there's a note here that it is not working. Okay, the previous guy wrote it there. I said, I fixed it, proudly. I fixed it. Oh my, you should have seen the look on his face. That's $1 billion machine. Yeah. And we have an annual contract on that. The company does it. How dare you open it? But I fixed it. They don't care you fixed it. And my punishment was 1 month out of the lab. Okay? But after a lot of requests, they brought it down to me, I think 15 days or something. So then I realized now that when I talk to my students there, they know that this instrument will do this. This is where I put my input. This is the output. I have standard tables where I compare. Alright, a lot of data there. We compare, and I get to know about what I'm doing. They have literally no idea what is inside the machine. Believe me. Okay? So, good journals, they publish with a lot of these sophisticated results. But hardly any or very few of the students really know how the system is working. Unless you know, how can you explain the whatever your data coming out, you're trying to analyze that. If you don't know how the instrument is generating those data, it won't be a very correct explanation happening, right? But anyway, we are poor people, so we have to do that ourselves. So I found that when we started making these, our students, they learned a lot about the physics behind all these instruments that are being developed, and that actually added to some benefit. Anyway, I think everybody knows about it. Like I just wanted to mention this, that nanomaterials have been used for centuries, right? In fact, thousands of years. And these are precisely through experimentations, or rather, it's accidents. Right? How glass was discovered. What is the raw material for glass? Silica, that is sand. Right? It's simply sand. Even for your semiconductors, your transistors, the source material is sand. Can you even think about it? Sand giving a transparent something? It's very difficult to think about. Nobody would start an experiment like this, but they were doing something else. They were heating up sand for a different purpose, and they see this transparent thing coming out. All right. So something like that might have happened. So if you look at this cup, those who haven't seen it, it's called Lycos cup. This was the magic. This was way back, 490 AD, right? So more than 15, 1700, 1800 years back. So it will belong to a Roman emperor. And of course, the Roman emperor's name is not Lycurgus. Okay? So Lycurgus is a character from the mythology. Okay? So he did a lot of wrong things. So these creepers, you see that guy here? This one? He will be pulled down by creepers. That's called ambrosia. God was so upset, pulling down into hell. Okay? So this guy name is Lycurgus actually. So this was used by the Roman emperor for drinking wine, and at the time it was like a magic thing, and people used to throng to just see this cup. Right? Why? Because now if you look at it now, see you are seeing it green in color, right? It's green. This is happening because of the light reflected from the surface. Right? So light is hitting the surface, coming to our eyes, and you're seeing it green. Now you take it and place it near a window, let the light pass through. Alright? So then you'll see a totally different color coming out there. So 2000 years back, this was magic. Right? So the transmitted light gives it a crimson color. And of course, in the early 1980s, nobody knew the phenomenon what was happening. Only in the early 1980s, when we developed the microscopes. Okay? We have scanning tunneling microscopes, electron microscopes. All these allowed us to zoom into that 1 billion times maybe and see what is inside there. And we found out now that these are only gold and silver nanoparticles. They are nanoparticles, right? Embedded in a silica matrix. And these gold, you might ask me why it's not golden if it is gold, or why it's not silver if it is silver. Because at the nanoscale, gold is not golden. Okay, silver is not silver. Gold can be anything between red, going down to even gray. And silver gives beautiful blue, green, pink, yellow, these colors you'll see. Now why, again I come to that, but this happens in metallic nanoparticles. You see various colors depending upon the shape and the size. Okay? Getting bored? Yeah? Okay, let's take a small.
Excuse me.
Yeah, you can.
How at the time Roman people know to isolate this?
Yeah, very good. That's what I was saying. It might have been an experiment. They know that if you do like this, this will come out. But they didn't know that they were. Only the
Process will be interesting.
yeah, definitely. This is something really worth studying how they did that. But personally, I think it was pure experiments. Just doing something, all of a sudden that happened. Maybe they were using some gold to make it golden, it became red. And they said, okay, if we do like this, add gold, it will become red. Something like that. Anyway, so let's look at something else because I think I'm already putting you guys to sleep, singing a lullaby. But Rashi is very nice to give me the first session because all my life I have always given the post lunch session. After having rice, it's very difficult to people have it. But anyway, a video at Assam, Harry Crosby, so let's quickly look at a video just to break the monotony. This video I keep showing you. It's an old video, but for those who haven't seen this, might be interesting. That's one video. Alright, so I love to show this video because my research group The first it was in Don Bosco, then I moved to downtown. There also we have now built up a lab and my PhD students are coming in. So I love to show the video because whatever research is shown there, most of the things we are doing here in our labs using programs and technology. We don't have sophisticated facilities like Cambridge. This was made at Cambridge together with a company called Nokia. You all know Nokia anyway, the cell phone company, right? So Nokia and Cambridge made this about 10 years back. I still have to show it. Just to demonstrate what nanotechnology can do to existing systems. Right? So your cell phone. Are you happy with your cell phone or whatever the services you are getting through your cell phone? Are you happy with it or do you want more? Right? If you want more, what more do you want? What more can your phone give you? Right up you. Video में तो पढ़ो समझे video itu ini soalnya itu. Some of you may have already seen this, but let's quickly have a look. It's a phone that was designed 10 years back by Nokia with research support from Cambridge University, right? And they tried to develop a futuristic phone which, apart from calling, can give a lot more things. So that's a typical thing, calling through your phone. Bluetooth is nothing new. You use Bluetooth every day, right? But this might be slightly new. Foldable electronics. So they are calling this as Morph. Okay? The model name Morph. So it's simply the use of law of nanotechnology. So if you look at this, the fruit, the apple, this fly can detect it immediately because of some sensors on its head. Same thing we are replicating. This is a top-down process, that's why it looks so beautiful. Right? But we are replicating those sensors and we have made them even more efficient. So sensing using nanomaterials is excellent because nanomaterials can give a lot of surface area. Right? A lot of surface area. So for sensing, you need surface area anyway because whatever you are trying to sense, it has to go and stick. So if you see here now we are zooming the phone surface. Here, zooming further, you see these rod-like structures. We are constantly doing this in our lab. We have developed many sensors using these type of rods, right? So these are capable of sensing. So it's much better than the nose because initially it's smelly because we are not sure whether it is rotten or not or has the rotting started. But your phone can tell you that, yeah, whatever you are eating, is it okay or not for the consumption. The biggest problem with our cell phones, especially my phone, I don't know why. I spend a lot of money on the iPhone. You need to keep it charging at least twice a day, right? Mainly because, like I said, battery technology is not enough to support us. But think about it, the phone you don't need to charge. Anytime some light falling on it, it will automatically charge. And not only the cell phone, it can even be big buildings like you see this one. This type of solar cells, they can be transparent, right? So you can put it, your glass itself can be a solar cell and think of about how much energy can be generated. But like I said, they're still not giving the efficiency we would want to have, and that's why it's still under research. Okay? A couple of my students are working on this area. Then this is the replication of the lotus leaf. See? The phone never gets wet. You put it in a bucket of water, nothing will happen. Right? Simply through nanostructuring of the surface. So you see this is zoomed in 100,000 times magnification. You see these type of structures, which sort of gives that situation like a lotus leaf. Right? So the water droplets do not get the chance to overlap. That's why it's self-cleaning and it is waterproof. Then of course the electronics that you need to stretch. Your typical electronics they will break. I mean the wirings will break because it's metal mostly or polysilicon. They will break, it will bend. Okay, but we have wires now that can take that extra load of stretching, right? Because they're extremely strong and they will not break down. Okay, so you can fold your phone nowadays. We have already seen these foldable phones. The screen itself folds, right? Previously, all the foldable ones, the screen was separate, but there were two screens. Now, the screen itself folds, right? So that's also happens because of nanomaterials. Transparent electronics, we already have the transparent from Samsung, also from Apple, because electronics can now be transferred, right? So this is unlike silicon. Silicon is not transparent. So our integrated circuits they are not transparent, but now we have developed semiconductors that can do this. So for haptic surfaces, basically surfaces that appear 3D even though it is 2D, okay, those are again signals that can be transmitted through nanofibers. Right? So we now have come to the age of wearable electronics. Right? So mainly because we can fold electronic circuits now. So that's fine. The phone uses the Bluetooth for calling, and then see uses it as a bracelet that will match with any part of a dress or the bag, right? So that's wearable electronics, right? So your cell phone. We never think of these functionalities in a phone, but this is possible, okay, with the use of nanotechnology, right? Can you go back to the slides? Okay, so any questions? Feel free to stop me. Stop me not. Even if you don't want to ask a question, you're too tired or sleepy, stop me also. Let's just have some transfer of knowledge. I've been working on this for so long, so maybe I'll know a little bit more than many of you. But then, of course, you are also aware. So we can have a nice interaction. I want to show this because, when I started my work, I knew nothing. And my boss was telling that you need to make some very good quality crystals. Crystals are basically materials that are atoms are nicely arranged in the right position. Right? So again, I asked how you don't have facilities, you don't have this because everywhere I studied all those very expensive instruments being used. Then you will say go to nature. So I started calling Mother Nature after that. So every time I was developing new materials, I was like, nature is something similar or not, right? Because nature doesn't have those facilities. And I came across this article. This photograph was there. So these are actually calcium sulfate crystals, right? We call them as gypsum. That's a typical name, gypsum. So these are huge crystals. Some are about 10 or 12 feet long, right? And these light colors are because of light. So people just put on some colored light because it was 1,000 feet below the surface. Right? They found a cave, and in that cave they found these crystals. And when they actually took out pieces and studied them, they found that they are perfect crystals. That means all the atoms are in the right positions. Okay? If they are not, then we call it as a defective crystal. But if they are all in the right position, then it's a perfect crystal. So these are all perfect crystals. And how that happened? How nature made these beautiful crystals there in a cave with no instruments, nothing. This is because there's a lot of humidity there, close to 95% or 98% humidity. So these people who took those photographs, they actually run in, click, run out, because otherwise they will get dehydrated. With so much of humidity, it was impossible for people to survive. So nature made these, so it obviously shows that if you have intense humidity, crystals can be formed. Right? The temperature was about 70 or 75 degrees inside the cave, okay? Because maybe a volcanic effect there. So this was my beginning of making crystals. Believe me, after that I made so many beautiful crystals, all in water at about 90-95 degrees centigrade. I mean, if you can increase the temperature further, it will be even better and faster. But water, boiling point of water is 100 degrees centigrade. So you cannot take it beyond 100 degrees centigrade. Once you put some salts there, it anyway won't go to 100 degrees centigrade. So all these we made around 90-95 degrees centigrade. Okay? But then, if you want, you can actually take it further. By how? You remember all those equations we studied in chemistry, right? T1 V1 by T1 is equal to P2 V2 by T2. There's a constant relation with pressure, volume, and temperature, right? That means if you can increase the pressure, you can increase the temperature also. Water will not evaporate. See, water is evaporating at 100 degrees centigrade at 1 atmospheric pressure, right? This is the, what we can say the ambient pressure. But if you seal it so tightly, okay, that nothing comes out from there, then if you increase the temperature further, even water will not evaporate. Alright? So that's why I even made something in water at around 120 to 140 degrees centigrade also in a sealed chamber. Right? It has to be very, very tightly sealed. But anyway, so a lot of things happen at this temperature and in water and at normally room temperature. And we call this process as hydrothermal process. Hydro means water, thermal means heat. So basically in water, with some amount of addition of heat, we get beautiful crystals like this. Right? So that was the study, and I made some beautiful crystals also after that. Let me skip all this. Alright, anyway, what we are talking about now is that this crystal, see, we talk about the surface. Now this is a big one. Let me cut it down, take it to nano size. If you're taking to nano size, the surface area will start increasing, okay? So, this is the idea. So you take some amount of mass, if you have a specific volume, right? As you start making it smaller and smaller and smaller, with the same amount of mass and the same amount of volume, if you add up into the same, then the surface area that is available for you increases tremendously. Right? And that's why we said it's perfect potential. You see, this is 6 centimeter square was the surface area. Take it down. Now we have made all these cuts. It became 24 times more. Oh, sorry, 4 times more than this. And if you go to nanometer, this nanometer cube from here, you are getting about 20. So that's maybe 3 million times increase in the surface area. The same amount of material, same amount of mass. Okay? That's why you see how much amount of sensing can be done, or even some other environmental manipulation process. Anything that is the surface, this is the perfect material. Okay. So that's about it. The key thing is the surface area, right? Huge amount of surface area, and we will talk about the atoms on the surface, right? I never loved chemistry. I was actually hated chemistry and biology, but now I'm doing a lot of chemistry and biology. So I know it's difficult. I remember my mother was very keen that I become a doctor. And I know very well that I cannot become a doctor. Okay? Now I can quite adaptable now, but previously small amount of blood, my head will change. This time when I had this accident, my leg, this part actually came off. I could see my bones. When I got up on the road, I could see my bones inside, and there's blood everywhere. People were like looking at me like they didn't know what to do. And I was instructing everybody, do this, do that. So somehow I think I come out of that and not giddy anymore seeing blood. But at the time I was. So I hated biology. I couldn't remember those names. Then, my mother sort of compelled me, but quietly I, signed in for advanced mathematics we had at the time, 11 and 12. So there's no possibility of going for a doctoral, doctor or become a medical doctor. Then I remember one day when I was in Thailand, I called up my mother and she was asking what are you doing. And one question she would always ask is how many papers do you have now? Okay, how many research papers? And because she said my whole life I had published only 18 papers. Okay, my whole career. She was a professor in Goa University. So whole career she had 18 papers, good papers. She was in botany. And every time she asked me, I used to add at least 6, 7, 8, 10, something like that, because my papers were coming in. So now it's crossed. I think my journal papers have crossed more than 100. Okay. So she used to say, no, then one day she asked me, what are you doing now? Is it research? I said, yeah. So what are you working with? I said, Aspergillus niger. That's a fungus, okay? So I was trying to make some conducting wires using Aspergillus niger as a template so that I can put it inside the heart here to basically power pacemakers. Because pacemakers we have to take out after 7, 8 years and we have to replace the battery. So we said let the heart charge it. Anyway, so I told Aspergillus, she said, what? When did you start loving biology? Okay, now I have gone interdisciplinary. So nanotechnology is very much interdisciplinary. So things I didn't like before, they became my passion. So chemistry, I always hated, but we are keeping the chemistry low here. But then it's very simple to work with slight variations in the conditions to make this type of nanostructure. Beautiful nanostructures you can make. I'll show you a few, same material, but you can make them in various forms, various sizes, various shapes. Okay? Simply by some change in conditions at the crystal's form. Okay? Anyway, you're getting bored?
10:30 evening, 10:30.
10:30?
30.
10:30 already we keep doing this.
No, 23.
Keep going. Move over to 27. How come? Because I know the reason. This watch was presented to me by my son when he was 5 years old. Okay? From the savings he got from everybody gives some amount of money sometimes when we come to India, and he was collecting. And then one day he said, I think you need a good watch. So he and his mother somehow went and bought this one at that time. So it's so close to my heart, I still wear it. So it's, he's 21 now. Okay, so it's 16-year-old watch. So understandable that it might go a bit fast. तो 5 मिनट है ना केवल 10 मिनट ऐसा तो break long. Okay, so in the next session I'll discuss a little bit about how we can make some of these nanomaterials and what type of applications we can actually go for. Okay, we have done many applications, and interestingly, the same material can be used for various applications, right? Like one material, we have been using it for as a sensing material. We have been using it as a purification material. We have been using it in antenna. For instance, I have been using this in signal transmission. Right? The same one, another of my students is trying to make what we call as fast healing bandages. Okay? That means instantly the blood clots. When I had this accident, she was there with me most of the time. She said, sir, I believe this. You actually needed it. So they want to complete her work. So we did some studies and all those. Something that will instantly clot the blood. Again, the same material. Okay? One of my students before made a sensor to test the quality of food in packages. Mostly meat, fish, this type of things that quickly gets bad. So same material used there. But it's all sweating or taking into advantage different properties of the same material. Alright? I will discuss a bit of that after tea. Right? So yeah. Solids. No, see, when you are going in a gaseous form, that's a molecule. Right? And we have something that is not molecule. In the sense that it can be molecule, but at least a few hundreds or a few thousands of molecules together. So it automatically becomes solid. So they will be suspended. So another small example that I can quickly tell you before I say this is for the tea. like I said, one word stabilizer. Okay, they need to be separated nicely, otherwise the agreement will fall down. So, a beautiful example from nature is milk. Right? Milk is a colloid. We use a term called colloid. Colloid means some particles suspended in a liquid. Alright? And they will retain the shape, size, everything. Unless something destabilizes the whole. Alright? So, milk, we make cottage cheese from. You know what's cottage cheese? Paneer. So, how do we make paneer? Any idea? Would you make paneer? How? We can add something, lemon maybe, or vinegar or something. So what happens? Initially it was in a stabilized condition. That means there are a lot of charges, electrostatic charges sitting on these particles. Okay? And they will repel each other, they won't come together. The moment we added some extra charges, okay, these are acids. Right? So they will have H plus. So that destabilizes the whole thing and agglomeration starts. And they will settle. Same thing happens with the nuclear that they are making. We can destabilize it. So add some charges to it, you'll see everything inside now. And that is another beautiful thing we can use for sensing. I'll show you a couple of my sensing work where we change the size of these particles. Say gold particle, it can be different colors based on the size. So if I make, say I have 15 nanometer size particles, and because of the presence of some polyethylene, they become 25 nanometers, then automatically you see a change in the color. Right? And that's visible to your eyes. So we made some beautiful sensors to test metal contamination in water. Right? So I'll show you some pictures after the feedback. Keep over us. So let's take a break. Okay? And I don't know after how long it is.